In this lecture, we're going to look at the sun's symmetrical path across the sky. The fact that the sun travels in a symmetrical path across the sky is an observation of particular importance for our purposes. So let's discuss this symmetrical pattern. What happens is the sun rises in an easterly direction at a rising angle of approximately 90 degrees minus your latitude. As the day wears on, in the northern hemisphere, the sun arcs across the southern sky, bearing due south at local apparent noon, otherwise known as land, which is not necessarily the same as clock time, but a time exactly halfway between the time of sunrise and the time of sunset. After land, the sun continues toward the west, ultimately setting in a westerly direction, once again at an angle of approximately 90 degrees minus your latitude. Also, the sun will set at the same number of degrees north or south of west as it rose north or south of east. If the sun rose due east, it will set due west. Now, I just described the northern hemisphere. In the southern hemisphere, the sun likewise rises at an angle of, or an approximate angle of 90 degrees minus your latitude. And as the day goes on there, it arcs across the northern sky, bearing due north at land. And then after land, the sun continues toward the west, ultimately setting in a westerly direction at the same approximate angle of 90 degrees minus your latitude. And once again, southern hemisphere, northern hemisphere, it doesn't matter. The sun will set the same number of degrees north or south of west as it rose north or south of east. We want to look now at the sun's maximum daily altitude and how that changes with the seasons. Looking at this drawing here, for example, you will see that the sun's highest altitude is in the summertime. And we're in the northern hemisphere now. So when we are at the June solstice, for instance, the sun rises as far north of east as it will ever rise for any given latitude, and sets as far north of west as it will ever set for that same latitude. So here you see the sun rising to the north of east, arcing high in the sky, and coming down and setting to the north of west. As we approach the equinox, the sun rises in the east, goes a little lower in the sky, and sets in the west. And as we are in the winter time, the sun rises south of east and sets south of west, and its arc across the sky is smaller still, and the sun's maximum altitude is even lower in the sky. Looking now at the southern hemisphere, you can see on the December solstice, which is the summer solstice, the sun rises south of east, makes an arc across the northern sky, and sets south of west. Then on the equinox, it rises due east, makes a bit lower arc across the northern sky, and sets due west. And then on the June solstice, the winter solstice down south, the sun rises north of east, arcs across the northern sky in a low arc, and then sets north of west. You see now how the seasons affect the sun's altitude, and there is another factor that affects the sun's altitude, and that is the latitude. The sun can get a lot higher in the tropics than it does in the Arctic or the Antarctic. Therefore, the sun's rays hit the tropics much more directly than they do at either pole. This is why it's warmer in the tropics than at the poles. It all has to do with the angle at which the sun's rays strike the Earth. It's more the direct rays striking the Earth that create warmth and not so much the additional daylight. I mean, in both the Arctic and the Antarctic, there's solid daylight for half the year, and yet it never really gets warm in either of those places. Speaking of the poles, navigating at either the North Pole or the South Pole can, I understand, be challenging for a variety of reasons. First of all, compasses do weird things up there. Plus, the extreme cold can make keeping a battery-powered GPS alive a real challenge. Then take into account the fact that you have to push tiny buttons with big heavy gloves on. Well, as you can imagine, even doing simple things in such a frigid environment isn't easy. Navigating at either pole is a specialty, and if you're going to go to either pole, you really should get some special instruction on navigating at those places. This course isn't designed to include polar navigation. But since we're learning about the workings of the sun, let's see how it works at the North Pole. The pole is shrouded in seasonal darkness until the day of the vernal equinox, when it just peeks out over the horizon. But instead of rising higher in the sky, it simply skims the horizon all day long. The next day, the sun is a bit higher in the sky, but still skimming the horizon. As the season wears on, the sun gets higher in the sky each day, but maintaining each day all day long virtually the same altitude. Finally, on the June solstice, as you see here in this picture, the sun reaches its maximum altitude of 23.5 degrees above the horizon. And at that height, it remains all day long, circling the great round of the horizon in a clockwise fashion. After the solstice, the sun circles a bit lower each day until the autumnal equinox, when it once again skims the horizon all day long. After the autumnal equinox, the sun disappears under the horizon, and following a bit of twilight, the pole remains dark once again for 6 months until the next twilight period before the sun rises yet again on the vernal equinox. Going now to the South Pole, you see the sun works similarly, but the seasons and the sun's directions are reversed. Remember, you're essentially seeing the universe from the bottom of a big spinning basketball instead of at the top. At the September equinox, which is the southern hemisphere's vernal equinox, the sun peaks above the horizon. And just like it does at the North Pole, instead of rising higher in the sky, it simply skims the great round of the horizon all day. With each passing day, the counterclockwise circling sun rises slightly higher in the sky. Finally, on the December solstice, the southern hemisphere's summer solstice, the sun reaches its maximum altitude of 23.5 degrees above the horizon. There, it travels around the horizon at 15 degrees per hour. After the solstice, the sun sinks slowly lower in the sky until the time of the March equinox, the southern hemisphere's autumnal equinox. The sun once again skims the horizon all day long. After the equinox, the sun dips below the horizon, and after some period of twilight, the South Pole sinks into months-long total darkness until the sun once again approaches the horizon around the time of the next September or vernal equinox. Before we leave off talking about how the sun works, let's go to the tropics and talk just a bit about how the sun works there. And of course, in the tropics, the sun still rises in an easterly direction and sets in a westerly direction. But depending on your latitude and the time of the year, the sun can pass you at midday either to the north of you or either to the south of you. And this could be in the same place. In one place, for instance, depending on the time of year, the sun might pass high overhead and a bit to the south, and in that same place, at another time of year, it might pass high overhead and a bit to the north. As an outdoorsman, the knowledge of the workings of the sun has been a big help to me. I think it'll be a big help to you, because the more you can understand about your environment in the great outdoors, the better off you'll be. Now that you understand some things about how the sun works, we get to turn now to the enjoyable task of learning to find direction from the sun. So let's move on to the next lecture.